In this video, we're going to talk about autonomous equations, phase line portraits, and stationary points or equilibrium solutions. To begin, we'll say that an nth order differential equation, so an nth order equation, the nth derivative of a function y, which is an unknown function of t, is expressed in terms of the independent variable, the function itself, and its various derivatives up to order n-1. We'll say such a differential equation is autonomous if f does not depend on t. F does not depend on t. A first order ordinary differential equation is autonomous then if it can be written y prime equals f of y. No t on the right hand side. So that's what we mean by a first order autonomous equation. Now, such an equation is obviously separable. There are no t's, so we can separate the variables. However, finding a formula solution may be problematic for two reasons. And let's see what those two reasons are. First of all, if you separate the variables, you get dy over f of y equals dt, and you're immediately confronted with the need to anti-differentiate 1 over f of y. And of course, depending upon the function f, this may or may not be possible. But even if you can do it, let's suppose you can get some nice elementary function g of y, which has a derivative equal to f. Then, of course, the formula solution becomes g of y equals t plus c. So you have an implicit solution, and you may or may not be able to solve that for an explicit function of y in terms of t. So you may have two problems. You may not be able to do the anti-differentiation, and you may not be able to solve the implicit equation for y as an explicit function of t. So what do we do? What we will do is develop a rather elementary yet surprisingly powerful method, a graphical/qualitative method, to describe the nature of the solution functions even though we can't find formula solutions. So let's suppose we start off with a first order autonomous equation. We always presume that the existence and uniqueness theorem applies. So f is a smooth function, its first derivative continuous. We can't find formula solutions, but we know f, so let's put that to use. Let's look at its graph. So for the sake of argument, let's suppose that f looks like this. This is the y-axis, here's f. And let's suppose f has a graph something like this. So that's f. And what we will see momentarily is that we are able to say something about the nature of the solution curves purely from the knowledge of where f has zeros and what its sign is in between. So here in this case we have 3 zeros, this point, and this point. Let's label them. Let's call this one A, this one B, and this one C. Okay, now I'm going to draw the ty plane. So here's the y-axis. And I'm going to draw a t dotted. Here's the t-axis. And now let's look, for example, at the point y equal a here. This is supposed to be a. It should be clear that the constant function y equals a is a solution to the differential equation. If y equals a, then y prime equals 0, and by assumption f of a equals 0. So the function y equal a is a constant solution to the differential equation. It's called an equilibrium solution. And the point A is sometimes called a stationary point. Similarly, b, y equal b, is a constant solution. It's b, and y equals c. Those are three constant solutions to the differential equation. Now let's look at points other than A, B, or C. Suppose I start off down here. Right? That's my initial value. That means I'm over here somewhere, and I can observe from the graph that f is positive there. That says that y prime is positive. The curve is increasing. The curve is increasing, and that's going to continue to be the case. And so I'm going to get a curve that looks something like this. Similarly for any point down here. On the other hand, suppose I start off at t equals 0 for a value between a and b, a point like this. Right? Then f is negative there. Y prime is negative. The curve is decreasing. And so I'm going to have a solution curve that looks something like this. So that's what the solution curves look like in between A and B. Between B and C, f is positive, so the solution curves are increasing. And finally, for initial values above C, f is still positive, so the solution curves are increasing. So there's my solution curves. At least they look roughly like that. I'll make a few more comments. The equilibrium points are assigned a certain nature. This guy is called stable. Because if I start at a value a little bit different from A, the solution curves converge back to it. This one, for obvious reasons, is called unstable. If I start with initial values a little bit different from B, the curves go away, and this one is called semi-stable. On one side, the curves converge back to C, and on the other side, they drift away. And so it's kind of a nice method. I'm drawing the nature of the solution curves without finding formula, and I use purely the zeros of f and the sign of f at the points where it's not 0. Now, if you look at my diagram, I'm suggesting something about the max and min values of f having some implication for inflection points on the solution curves. I'm not going to dwell on that here. But what I am going to do is make 4 important points. So here they are. First point. The solution curves don't intersect. Why don't the solution curves intersect? That's purely because of the existence and uniqueness theorems. Existence and uniqueness theorem. If 2 solution curves intersected, that would say that I have 2 solutions going through the same point. So if I take that point as my initial data, I would be contradicting the existence and uniqueness theorem. So solution curves don't intersect. Second point, the equilibrium solutions are asymptotes. For non-constant solutions. Well, that's how I drew it here, obviously, for example, here. And that can be proven without too much difficulty, and you can consult the MATLAB book for that. There's a nice, simple proof of that fact in there. Third fact, the solution curves are constant or monotone. Either they're constant, or they're everywhere increasing, or everywhere decreasing. Also, a proof of that in the MATLAB book, but that's really obvious from the nature of the autonomous equation. And finally, the last point, the fourth point, is that if you extend to the left, you can do that. You can extend all these solution curves to the left. And then project onto the y-axis. Project all these solution curves onto the y-axis. What's going to happen? The constant solutions are going to project to these points. And all the other solutions are going to project to the entire intervals in between them. Right? All these solutions will project to that. The solutions between B and C will project to that. And so that gives rise to the concept of a phase line portrait. Phase line portrait. Let me say a little bit about what that means. It means you should think of the points on the y-axis as tracing out the projection of the solution curves onto the y-axis. And what will the points do? Points at A, B, and C won't do anything. And a point here, starting here, will just mosey on down infinitely long until it gets at infinity to the point A. So how does a phase line portrait look? This is a portrait that you've seen in the notes. It looks something like this. So I'm going to draw the y-axis horizontally now. Here are the points A, B, and C. This is A, B, and C. And then to the left of A, the points are going like this. And between A and B, they go like that. Between B and C, like this. And above C, they also go in that direction. So there's a phase line portrait for this differential equation under the assumption that the graph of f looks like this. What does a phase line portrait do for you? Well, first of all, it identifies the stationary points, or equivalently the equilibrium solutions. Then it tells you the long-term behavior of the solution curves that start at points other than the stationary points. And finally, it summarizes for the stationary points the nature of their stability. Okay, now I'm going to look at a concrete example, one that's rather different from any that are in the notes. And the example is the following. Y prime equals e to the y plus 1 minus 3y squared. Clearly an autonomous equation. Right-hand side is a nice function of y, but it's one that you can't deal with symbolically. Trying to integrate the reciprocal of that expression is, by any of our methods, is hopeless, and MATLAB fails as well if you try with dsolve. So what am I going to do? I'm going to do three things. First, I'm going to draw this curve. Combination of a sine of an exponential and a polynomial. Second thing I'll do is find its roots. And the third thing I'm going to do is, well, I'm going to draw the general nature of the solution curves, and I'll do that by drawing its vector field. And so it should be obvious I'm going to use MATLAB to do all three things. After which I will come back and then I will draw the phase line portrait for this first order autonomous ODE. Okay, here's a nice M file to do exactly what I just indicated I was going to do. Here's the differential equation. Y prime is e to the y plus 1 minus 3y squared. I start off by clearing everything. And the first thing I'm going to do is graph that function. So I'm doing it using EasyPlot. Here's the function. EasyPlot's default variable is x, but I'm labeling the graph y and f. Let's run it. Still in the first section. Okay, there's our graph. So looks somewhat like a cubic. Well, it's not because of the exponential. How many times does it cross y equals 0? Y equals 0 3 times. 1, 2, 3. And it looks like those values are, I don't know, about -1, maybe 1 point something, and a little bigger than 3.5. Notice I labeled it y and f. Okay, so the stationary points. As I say, we see from the graph there are three equilibrium solutions. They appear to be at roughly x equal -3/4, 5/4, and 3 1/4. and I use F0 to find them more precisely. I set format long, so that will have lots of decimal places. And here's the format for the F0 command without any intermediate function. I just put in the expression right here. Let's get the 3 values. I ran it. It did it immediately, but I have to bring up the MATLAB window. And there are the 3 values. About minus 0.7, about 1.2, and about 3.7. So now I drew a vector field. I have my t variable going from minus 1.5 to 5, and y goes from minus 1.5 to 4.5. There's the expression, normalized as usual, and I'm using mesh grid and quiver, and let's see what we get. There it is. There's your 3 equilibrium solutions, minus 0.7, 1.2 roughly, and 3.7. And this guy is clearly unstable. This one is stable, and this one is unstable. So I've done the 3 things I said I was going to do. I drew the solution curve, not the solution curve, the curve for the function f. I found its roots, and I found the nature of the stability points by drawing the vector field. Finally, here's our last page. There's the original differential equation. I graphed the right-hand side f. I found the roots. There are the 3 of them, approximately. Here's the vector field, and finally, here's the phase portrait that summarizes what we found, the 3 stationary points, or equilibrium solutions, and the direction of the solution curves in between. Obviously, the middle one is stable, and the 2 outside ones are unstable.